March 23, 1905, Pittsburgh, Pennsylvania. The catastrophic shearing failure that nearly ended mechanical press development would echo through American steel mills for the next 100 years. At the Allegheny Steel Works, Chief Engineer Robert Hartwell watched 47 tons of locomotive axle stock crack diagonally across its center as his revolutionary mechanical press applied what should have been a precisely controlled force. The sound of tearing metal reverberated across the factory floor as foremen shook their heads and signaled for the steam hammers to be fired up. European metallurgists had been right all along. Slow mechanical presses could never replace the proven power of steam hammer technology. The German consultants had declared mechanical pressing theoretically sound for small components, but practically impossible for heavy industrial forging. Too slow for production demands, too gentle for steel's stubborn resistance, too complicated to trust with the massive forces that turned raw billets into usable products. But in that catastrophic moment, as Hartwell stared at the ruined axle stock, representing $12,000 in wasted material and labor, he discovered something the European experts had never considered. The problem wasn't that mechanical presses couldn't forge steel. The problem was that American engineers were building presses like Europeans built steam engines when they should have been building them like Americans built everything else, to last forever and work perfectly every single time. The morning shift whistle cut through the cold Pittsburgh air in February 1902 as Hartwell stepped onto the factory floor of Allegheny Steel Works. The sound that dominated every steel mill from Pennsylvania to Ohio was the rhythmic pounding of steam hammers, massive iron rams driven by steam pressure, crashing down on glowing steel billets with earth-shaking force. Hartwell pulled out his pocket watch. 6:15 in the morning, and the hammer crews had already been forging for 45 minutes. The foreman, Michael O'Brien, stood watching his team with the weathered face of someone who had spent 31 years in steel mills. Each hammer blow delivered between 8 and 40 tons of impact force, depending on steam pressure and the operator's judgment. The process was brutally simple but required extraordinary skill. A glowing billet of steel, heated to 2,300 degrees Fahrenheit, was positioned under the hammer. The operator released the steam valve, sending the massive hammer head crashing down. The steel deformed under the impact, spreading and elongating according to the force applied and the number of blows delivered. "Mr. Hartwell," O'Brien called out over the hammering noise, "you're here early to watch real forging work." Hartwell approached the main steam hammer where two workers were shaping a railroad axle. The mathematics were simple, but the implications were staggering. Pittsburgh's steel boom demanded 3,400 forged components daily. Axles, crankshafts, armor plate, structural beams. That meant 280 skilled hammer operators working 12-hour shifts, each blow requiring split-second judgment about force, timing, and steel temperature. The waste alone, components cracked by excessive force, pieces warped by uneven heating, forgings weakened by inconsistent blows, averaged 34% of every production run. The rejected material represented not just wasted steel, but wasted labor, wasted coal for reheating, and wasted time that pushed delivery schedules further behind demand. "How many blows for that axle, Michael?" Hartwell asked, though he had been counting. 47 blows if McCarthy keeps his rhythm right," O'Brien replied, pointing to the hammer operator who was carefully judging each impact. 52 if he misjudges the temperature and has to reheat. See how he's watching the color? That's what separates a master forger from a novice. You can't teach that kind of judgment to a machine." Hartwell nodded, but his mind was calculating. 47 blows per axle, 12 axles per shift per hammer, $8.30 in labor, and steam costs per finished piece. The numbers that kept him awake were even more troubling. Steam hammer forging cost $23.40 per ton of finished product, and the quality variations meant that critical components like locomotive axles had a 19% field failure rate within their first 5 years of service. Across the factory floor, Hartwell noticed a group of well-dressed men examining a cracked crankshaft near the quality control station. Their expensive suits and formal bearing marked them as European engineering consultants, the type of technical experts that American steel companies increasingly relied upon for major expansion projects. One of the consultants, a stocky man with steel-gray hair and a thick mustache, approached O'Brien's hammer crew. Hartwell recognized him immediately. Professor Klaus Brenner, whose textbook on industrial forging was considered the definitive authority in metallurgical circles. Brenner watched the forging process for several minutes, occasionally asking questions about temperature control and impact force. His face showed the satisfaction of someone witnessing confirmation of long-held beliefs. "The fundamentals are correct," Brenner announced to his colleagues in accented English. "However, mechanical pressing remains unsuitable for heavy steel work. Proper forging requires the hammer's decisive impact, the ability to overcome steel's resistance with concentrated force that no slow-moving press can match." Hartwell stepped closer, unable to resist joining the conversation. "Professor Brenner, what if a mechanical press could apply force more gradually, allowing the steel's crystal structure to reform without the shock damage that hammer blows create?" Brenner turned toward Hartwell with the patient expression reserved for well-meaning amateurs. "Mr. Hartwell, isn't it? I've read your proposals in the trade journals. The problem isn't gradual force application, it's production speed. Watch Mr. O'Brien's crew. They complete one axle every 11 minutes. Your mechanical press proposals suggest 28 minutes per piece. American industry cannot afford such inefficiency." Hartwell had to admit that Brenner's math was accurate. Current mechanical press designs were indeed slower than steam hammers. But he also saw something the professor seemed to overlook: the quality consistency that mattered more than raw speed. "Professor, what if we could eliminate the 34% rejection rate? What if every forged piece met specifications without the variations that steam hammers inevitably produce?" "Then you would have consistent mediocrity instead of occasional excellence," Brenner replied firmly. "Steel forging is an art as much as a science. The hammer operator's judgment, his ability to read the steel's temperature, adjust force mid-strike, compensate for material variations, cannot be replicated by fixed mechanical systems. This is why European mills employ master forgers rather than experimental machinery." The disaster that would teach Hartwell everything he needed to know about mechanical forging began at 9/7 on a Monday morning in October 1903. His first prototype press sat silent on the factory floor, surrounded by cracked and warped steel components that had cost him $63,000 in ruined material and nearly destroyed his professional reputation permanently. Hartwell crouched beside one of the failed forgings, a locomotive connecting rod that had sheared cleanly through its center under what should have been a controlled pressing force. The fracture surface told a damning story: brittle failure with no plastic deformation, indicating that the steel had cracked suddenly rather than yielding gradually as proper forging required. The Pittsburgh Gazette had already run their headline: "Hartwell's slow press proves slower than expected, produces only scrap." Professional humiliation was expensive, but the engineering lessons hidden in this failure would prove invaluable. Back in his workshop 3 weeks later, Hartwell spread dozens of failed components across his examination tables. Each piece revealed specific mistakes in his approach. Some forging showed obvious cold working. The press had applied force before the steel reached proper forging temperature. Others displayed the telltale signs of too rapid force application, with internal fractures that wouldn't appear until the component failed catastrophically in service. Hartwell opened his detailed testing logs and reviewed the data he'd collected during the failed demonstration. His press had operated at varying speeds between 0.8 and 3.2 inches per minute, depending on hydraulic pressure fluctuations and valve inconsistencies. Steam hammer operators, he had observed, delivered impacts lasting 0.04 to 0.1 seconds, creating force application rates that varied wildly but averaged extremely high. The breakthrough came when Hartwell realized he had been solving the wrong problem. He had focused on building a machine that could apply force slowly when he should have been building a machine that could apply force correctly. The difference was mathematical precision versus mechanical approximation. Hartwell began by calculating the optimal force application rate based on steel metallurgy. High carbon steel required specific deformation speeds to maintain proper crystal structure, slow enough to allow grain reformation, but fast enough to occur while the steel remained at forging temperature. After months of metallurgical testing, He determined that 1 to 4 inches per minute provided the ideal balance for most steel grades. The engineering challenge was maintaining that precise speed regardless of load variations, component size differences, or temperature changes in the steel being forged. Hartwell's original design had used a direct hydraulic ram system, which provided adequate force but allowed significant speed variations as the steel's resistance changed during deformation. His new design employed a massive mechanical system, a 40-horsepower electric motor driving a 12-ton cast-iron flywheel through a 47 one-gear reduction. The flywheel stored enormous rotational energy that smoothed out resistance variations, while the gear train converted the motor's high-speed rotation into the slow, powerful, absolutely consistent pressing motion that proper steel forging required. But speed consistency was only part of the solution. Hartwell's analysis revealed that force distribution was equally critical. Hartwell's failed prototype had used a flat pressing surface that concentrated force in the center of each workpiece, creating stress points that led to cracking. Studying the techniques of master hammer operators, Hartwell noticed that the best forgers rotated their workpieces constantly, distributing hammer blows across the entire surface to ensure even deformation. Hartwell redesigned his press platens to replicate this motion mechanically. Instead of flat surfaces, he created crowned platens with a precise 3-degree radius that concentrated initial force at the center, but gradually distributed pressure outward as the steel deformed. The platen geometry was calculated to ensure that every portion of the workpiece received proportional force throughout the forging cycle. Material selection became another crucial factor. His original press frame had been constructed from standard structural steel, which flexed slightly under load, creating imperceptible variations in force application. Hartwell replaced the frame with a massive cast-iron structure weighing 89 tons, so rigid that deflection under maximum load was less than 0.03 inches. The increased cost was substantial, but the improved force consistency justified every dollar. Testing the redesigned press required systematic comparison with steam hammer forging. Hartwell established a controlled protocol using identical steel billets, heating procedures, and final specifications. His new press produced components with grain structures averaging 94% uniformity and internal stress variations of less than 6. Steam hammer forgings from the same steel showed grain uniformity ranging from 61% to 80%, with stress variations averaging 20%. The mathematics were compelling, but Hartwell knew that factory managers would demand proof under production conditions. He arranged for a side-by-side demonstration at a railroad equipment manufacturer, where his press would compete directly against O'Brien's most experienced hammer crew. The test began at sunrise on a cold November morning. O'Brien's 3-man hammer crew established their familiar rhythm immediately, heat the billet to 2300 degrees, position under hammer, deliver 47 precisely judged blows, inspect, and repeat. Hartwell's press operator, trained specifically on the new forging protocol, began his first axle at exactly the same time. The initial results seemed to favor the hammer crew. Their first axle achieved proper dimensions in 11 minutes and passed all visual inspections. Hartwell's press required the full 28-minute cycle that his calculations had specified, and the finished axle appeared slightly different in surface texture than the hammer-forged piece. But as the day progressed, the advantages of mechanical consistency became undeniable. O'Brien's crew began showing the inevitable effects of repetitive work. Their hammer timing became less precise. Temperature judgments grew less accurate as fatigue set in. By mid-afternoon, 3 axles had been rejected for dimensional variations, and 2 more showed suspicious surface cracks that might lead to field failures. Hartwell's press maintained exactly the same performance throughout the entire day. Every axle required precisely 28 minutes. Every finished component achieved identical dimensions and surface finish. More importantly, metallurgical testing revealed that the press-forged axles had significantly superior internal structure, uniform grain patterns, minimal residual stress, and material properties that exceeded the railroad's specifications by 19%. The successful demonstration at the railroad equipment plant meant nothing to steel mill managers who had never seen Hartwell's press work. Throughout the winter of 1903, Hartwell discovered that superior metallurgy was insufficient to overcome decades of industry tradition. Factory superintendents who had built their operations around steam hammer technology viewed mechanical presses as expensive experiments that threatened both their workers' expertise and their proven production methods. Hartwell's first sales calls across Pennsylvania revealed the depth of resistance. Mill managers listened politely to his metallurgical data, examined his grain structure photographs, and inevitably concluded that their steam hammers worked adequately. Why risk production disruptions and capital investment on unproven machinery when experienced crews could deliver acceptable forgings using time-tested methods? The breakthrough came when Hartwell realized he was asking managers to make the wrong choice. Instead of demanding they choose between proven methods and superior technology, he would eliminate their risk entirely. Hartwell developed a guarantee that no mill manager could refuse: 90 days of free press operation with complete money-back promise if the machine failed to deliver cost savings and quality improvements. The first manager to accept Hartwell's offer was Thomas Brennan, who operated a mid-sized mill in Youngstown, Ohio. Brennan had calculated that his operation produced 340 tons of forged components monthly, with rejection rates that cost him $4,100 in wasted material and rework. Exactly the type of operation where mechanical pressing advantages would be most apparent. Hartwell personally supervised the installation of his press at Brennan's mill in March 1904. The machine arrived on 3 railroad cars, requiring a steam crane and reinforced foundation to support its 89-ton frame. Hartwell's operator spent 1 week training Brennan's crew on proper operation, temperature monitoring, and maintenance procedures. The results exceeded even Hartwell's expectations. Brennan's rejection rate dropped from 34% to less than 4% in the first month. Components that previously failed in field service began lasting their full expected lifetime and beyond. Most importantly, despite the press's slower cycle time, overall production efficiency increased because virtually every forging met specifications on the first attempt. Brennan's cost analysis revealed the true economic impact. Material waste dropped from $4,100 monthly to $470. Labor costs per ton decreased because the press required only 1 operator instead of 3-man hammer crews. Energy costs fell because the electric motor consumed less than half the coal equivalent of steam hammer operations. The total cost per ton of finished forgings was 27% lower than Brennan's previous costs, generating unexpected profit that more than compensated for trying new technology. Word of Brennan's success spread through the steel industry's informal networks faster than any advertising campaign could achieve. Mill managers began calling Hartwell directly, asking about press specifications and terms for trial installations. By autumn 1904, Hartwell had 11 presses operating across Ohio and Pennsylvania. Each successful installation generated additional orders. Managers who had initially been skeptical became enthusiastic advocates when they discovered that mechanical pressing delivered consistent advantages on every type of forging work. The telegram arrived at Hartwell's Pittsburgh office at 2:34 on the afternoon of March 23, 1905. The press frame cracked. Allegheny steel. Complete shutdown. Urgent assistance required. Morrison. James Morrison never sent telegrams unless the situation was catastrophic, and this one confirmed Hartwell's worst fears about the project that was supposed to establish mechanical pressing as the new industry standard. Morrison's Allegheny Steelworks represented the largest installation yet, a massive press designed to forge armor plates for naval contracts, the most demanding application in American steel production. Hartwell caught the next train to Pittsburgh, but he already anticipated what he would find. The press had been operating continuously for 6 weeks, forging 12-inch armor plates for the Navy's new battleship construction program. The work demanded maximum force capacity, 3,800 tons of pressing force maintained for extended periods as the thick steel plates slowly deformed to required specifications. The scene at the mill was exactly as devastating as Hartwell had feared. The press's main frame showed a hairline crack extending 14 inches from one of the main bolt holes. The crack hadn't failed completely, but it had propagated far enough that continued operation would risk catastrophic frame failure. The press sat silent, with a half-finished armor plate still between the platens, representing not just one ruined forging, but the suspension of an entire naval contract. Morrison stood beside the damaged press with Navy quality inspectors, their faces showing the particular stress that comes from explaining expensive failures to military procurement officers. The frame cracked during the 47th hour of a 72-hour continuous forging cycle, Morrison explained, as Hartwell examined the failure. Everything seemed normal until we heard the metal stress signature change. We shut down immediately, but the damage was done. Hartwell traced the failure systematically. The press frame, designed for normal intermittent operation with cooling periods between forgings, had been subjected to continuous maximum load cycles that generated heat buildup in the cast iron structure. The thermal expansion had created stress concentrations at the bolt holes, the weakest points in the frame design, where the crack had initiated. More critically, Hartwell discovered that the frame design included sharp internal corners at stress transition points, creating stress concentrators that metallurgical theory predicted would eventually fail under cyclic loading. His original frame design had prioritized minimizing material cost and casting complexity over maximum durability. The technical failure was serious, but the timing made it potentially fatal to mechanical pressing's reputation. Allegheny Steel supplied critical naval contracts, and any quality concerns would be investigated by military engineers whose reports would influence procurement decisions across the entire steel industry. Within days, the story had spread beyond Pittsburgh. Industry publications carried detailed accounts under headlines like "Mechanical Press Fails Critical Military Contract," "Steam Hammers Prove Superior for Heavy Forging." The Navy suspended Allegheny Steel's armor plate contracts pending investigation. Other mills with pending press orders postponed their decisions. Hartwell's order book, which had been growing steadily, shrank by 68% in 2 weeks as mill managers retreated to proven steam hammer technology rather than risk similar failures. But Hartwell saw in this disaster what his critics could not: the specific engineering weaknesses that, once corrected, would make his press design virtually indestructible. Working 18-hour days in his workshop, Hartwell began the complete frame redesign that would define mechanical press construction for the next century. The original frame had been a complex casting with internal passages and sharp transitions that minimized material but created stress concentrations. Hartwell's new design was almost absurdly simple: a massive monolithic casting with generous radii at every transition, no sharp corners, and wall thicknesses 4% greater than stress calculations required. The frame weight increased from tons to 147 tons, and manufacturing costs rose by 52%, but the redesigned frame could withstand continuous maximum load operation indefinitely. Hartwell's stress testing showed safety margins exceeding 300. The frame could handle 3 times its rated capacity before approaching yield stress. More importantly, the thermal mass of the heavier frame absorbed heat from continuous operation without significant temperature rise, eliminating the thermal stress that had caused the Allegheny failure. Hartwell also redesigned every other component with the same philosophy: build it so robust that failure becomes effectively impossible. The main gear train, originally manufactured with standard tolerances, was rebuilt with precision ground teeth and twice the normal face width. The flywheel was increased from 12 tons to 19 tons, storing enough energy to maintain pressing speed even if motor power fluctuated. The opportunity to prove the redesigned press came sooner than Hartwell expected. The Navy, desperate to resume armor plate production, agreed to test his new design at Allegheny Steel under the most demanding conditions: continuous forging cycles for 30 days, producing armor plate to specifications that steam hammers couldn't reliably achieve. The test began in November 1905, and the results exceeded even Hartwell's confidence in his design. The press operated continuously for days, forging 127 armor plates without a single rejection. The frame showed no stress cracking, no dimensional changes, no signs of fatigue. More importantly, the armor plate quality surpassed anything steam hammers had produced. Uniform thickness within 0.02 inches across 12-foot plates, grain structure so consistent that ballistic testing showed 23% improvement in penetration resistance. the Navy's metallurgical report became the definitive validation of mechanical pressing. Their engineers concluded that Hartwell's press produced armor plate superior to any forging method previously available, with consistency that eliminated the quality variations inherent in steam hammer work. Within months, every major naval shipyard had ordered Hartwell presses for armor plate production. Commercial success followed quickly. By 1908, 78 Hartwell presses were operating in steel mills across America. By 1915, mechanical presses had largely replaced steam hammers for precision forging work. The presses built in 1905, constructed with Hartwell's over-engineered simplicity, proved almost impossible to wear out. Many operated continuously for 60, 70, even 80 years, still forging steel in the 1970s and 1980s with their original frames, original gears, original flywheels. The irony was that what critics called too slow became the foundation of a century of American steel production, proving that building things right mattered more than building them fast.